What I'm going to be talking about today is hunting for backdoors in IoT firmware. The reason why we're okay with saying unprecedented scale is because the past year we've been scraping as much firmware as we can get from vendor websites. We have 76 that we archived so far, with close to 250,000 firmware images. We process this information all statically and automatically. So the process for doing automated analysis for looking for vulnerabilities is a really interesting and hard problem. We've kind of scoped that information or that sample set of particular problems down to backdoors for the purpose of this talk. But we'll kind of get into where we are. So Finite State is an IoT security company focused on building solutions that allows organizations to more confidently deploy IoT and manage them on the networks, and also understand the risks associated with doing so. So in order to understand how we can do backdoor discovery with firmware analysis and do it in an automated fashion, there's 5 steps that we need to take for this process. The very first one is understanding how much data we actually have to analyze and how much duplication is involved, because it ends up taking a problem that's really, really large and making it into a more tractable problem if we can deduplicate the amount of code that's reused in these devices. Then we'll talk about 6 backdoors that are and how they manifest in IoT devices, so we can get an understanding of what we actually need to hunt for, the types of signatures that are typically associated with backdoors. Then we'll talk about the power of correlation and how correlation, because of the massive amount of duplication, can help us find issues extremely quickly in other devices that you may not necessarily link together. Then we'll talk about how we do source code analysis and binary analysis. So first, let's go into the scale of data and duplication. First of all, the information that we've had focuses on a 3-month study of close to 9,000 IoT products. In that, we verified 4 IoT backdoors. The specific trigger for that backdoor is unique in 75 devices. And then we have 11 that we're working to verify that affect 107 devices. So that's between 1% and 2% or so of the devices that we actually analyze and tag have potential backdoors or verified backdoors. So as I said before, collecting firmware is a process that is typically done through scraping. There's a few ways of getting firmware. One of the things that we can end up doing is scraping the web for as much firmware as possible, partnering with OEMs to get that firmware, removing firmware from a chip on a device, or man in the middling and update process to acquire where that information is retrieved from and trying to retrieve it ourselves. So through scraping, we've been able to amass 224,000 firmware images. And if we take just those images that link to individual products during the scraping phase, that deduplicates about 30% or 70% of the overall amount. So it's 157,000 unique firmware images. This means devices like Polycom devices or MikroTik devices that have one firmware image that links to a lot of different devices could be the reason for having so much duplication in the firmware scraping phase. Is that when we scrape, we actually end up pulling that information from each product, but it all comes down as one unique image. Looking over at how much we actually extract from that, from the 157,000 unique, there are close to 35 million successful file extractions. That includes duplicates at this point until we deduplicate that phase. But the file analysis and metadata that happens are like where that information actually came from, where it exists in the file system tree, the MIME type is, things like that. The file analysis ends up being startup scripts like analysis to understand which projects or what executables are being kicked off. We also look for hashes and crack those if possible, things like that to understand default credentials on systems. So considering the 35 million files that come out of this, when we look at files or select file types that have security significance to us, these are the types of files we really want to analyze. When we look at executables, there's about 1.4 million that come out of this. Only 160,000 of those are actually unique, meaning there's a massive amount, 89.2% duplication. In fact, when I first queried these numbers for our database, I thought it was a complete joke, like this had to have been wrong. But we double and triple checked these numbers. And it's pretty insane how much all this stuff ends up being sort of bloated. So one of the things we did originally to stress test our system was to get as much firmware as quickly as possible. So we downloaded as much DDWrt as possible because it has so much firmware available. And we push that through the system to make sure that we can scale to a high number, even taking into account that DDWrt is only 5% of the total file nodes in this. It doesn't affect these numbers that much, meaning if we select individual devices, or device types, or manufacturers, it ends up being about the same amount of duplication. So if we consider all of the executable shared libraries, shell scripts, things like that that are important to us, and the amount of deduplicated files, it's about 91.7 duplication, percent duplication, which means if we're doing analysis, every file that we analyze, for the most part, is found in many other devices. So we can kind of essentially explode that amount and we get a lot more bang for our buck when you do automated analysis and we have so much duplication. So you might be asking, what are the other 30 million file types, right? The other file types are things like certificates and kernel objects, random scripts like Lua and Perl that might be on the system, and massive amounts of web content, depending on the IoT device. They have a web interface, and that generates a ton of content that isn't really interesting for us to analyze, like images and whatnot. There are certain things like HTML, being able to carve out certain types or certain scripts. That information lets us know how to interface with backend CGI scripts or binaries to elicit certain types of information into the system, right? So there are certainly other types that are actually interesting to us, but most of them we don't actually have to analyze because they don't really play a role in security. So let's take a look at how 6 different backdoors have been found in IoT devices and get a sense of what we really need to look for when we automate this. Now, this is pretty old. In 2015, Juniper put out a notice on their NetScreen firewalls. It was running Screen OS, and it was found that there was a backdoor that allowed a user to authenticate over Telnet or SSH without providing a valid username. You can roll your hand over the keyboard and then type in the string that's listed here. It's highlighted in yellow. So when this advisory came out, independent researcher claimed that they had found it a few hours later by looking through the firmware. HD Moore published a Rapid7 post the next day, also documenting exactly where this was. And essentially, the string comparison that actually happens during this phase looks very similar to the types of debugging strings that are just inherently existing inside of this firmware image. So they're trying to thwart any type of analysis that would just run strings or frequency analysis on strings to try to pull out outliers. The next IoT backdoor we're going to look at is double-tech GeoIP devices that had a login binary. The login binary, when you issue a normal request to Telnet into the system with a normal user, would just ask you for a password. But when you enter the DBL ADM or double admin username, it gave you a challenge. That challenge, as long as you know the algorithm, you can mutate the challenge code and type in a password that'll give you access to the system. Anybody who's ever done reverse engineering, like this is the very first thing that you work on to learn reverse engineering is crackmes, and this is a crackme. So whenever you see something like this, you can almost guarantee that a reverse engineer is not going to sleep until they actually solve this problem. So this is an example of security through obscurity and not security itself. Another one that was revealed in a Packet Storm post by Wadi has no CVE attached to it, and it turns out that a particular development device that they analyzed had this web shell, so it's dev HTM, and if you go to the web interface and type in /dev HTM without authentication, it'll prompt you for this very generic looking interface. It has 3 commands, config, sys, and sh. And when you type in sh, it drops you to a root shell and pipes everything back and forth between this dev.cgi binary. So at this point, you could type wget, pull down files, execute them. You can scrape NVRAM for passwords, which are the information that's redacted. This is from a live system on the internet. So this type of information clearly shouldn't be exposed to an authenticated user. The next issue comes from a network manager, CGI. Again, CGI handler, that's an ARM binary. It manages user sessions. So what happens is when you make a post request with a very specific command and flag value, it ends up creating a user session, but then never actually validates the user session if you apply a username admin to the cookie data. This type of problem is extremely difficult to find via automated analysis, especially static analysis. It requires an understanding of what the code that's being sort of like bypassed when this condition or these checks are actually valid, and that is hard to discern. So another one is very popular. I had an IP camera series that had a backdoor telnet, and I used the term backdoor pretty lightly here. This set of credentials were used in Mirai, and essentially what happened was they took BusyBox and during the login phase, prepended this string to whatever the normal credentials were. So if your username, password, or admin, the password would be admin, this string, and admin. Essentially what it does is anyone who's setting up a device and tries to make sure that no one can log in over Telnet or thinks that they have a secure system because their normal credentials don't work, don't understand that what's happened is this particular system has injected a phase between that to make sure it looks for this particular signature before logging in. The very last one that we'll look at before we go into more details here on correlation is this issue in ingenious devices. So there's a login.sh that's tied to Telnet connections. When you look at the startup sequence of this, Telnet started with a listener of the login.sh. Logins are jailed, so you have to actually log in with like credentials. But once you're in that system, the image on the left shows a jailed session. So you only have access to a few commands like sysstat, reboot, and etc. If you type in this MD5 hash here on the right, it drops you to the root shell. So it's not hard to find this MD5 hash. You can look at the reference and all that information is there. But what's interesting is that this undocumented command gives full control over the system when it's not supposed to be, right? So these are the types of things that we need to consider and look for. So now let's go ahead and talk about the power of correlation. When we talk about correlation, what we're trying to do is talk about earlier about deduplication. And we had a ton of duplicates, and that's accomplished through cryptographic hashing. So SHA-256 allows us to verify that files are exactly the same, and we can redo, we can reduce the sample set that we have to analyze. Fuzzy hashing enables correlation, so it means how similar are these two different files. AMA refers to approximate matching algorithms, and in 2006, Jesse Kornblum from Mantech, who's at Mantech at the time, came out with this paper called Identifying Almost Identical Files Using Context-Triggered Piecewise Hashing. By 2010, almost every single malware researcher on the face of this planet was using SSDeep, which was a product of that research, to perform correlation on malware samples. And largely since 2006 or 2010, like when all this started becoming popular, that's still seen today in these systems. So if you upload a sample of VirusTotal, you're given an SSD signature, and then you can use that to perform correlation on your own samples. So when we started looking at how correlation can be best used, we started looking at what's happened since 2006. Originally in the 90s, we had SpamSum, then we had SSD, then SDHash, MRSHv2, and then MRSHCF, which employs Cuckoo filters. That information was released in a paper in 2015. And essentially what we end up doing is using MRSCH because it gives us more finer granularity in tests that we've done. So this sample set of files here is to demonstrate the differences between SSD correlation and MRSCH, MRSCF. So at the very top BusyBox, these are the exact same files, and we'd expect 100%. On line 6, slight HTTPD and libUSB so4 are completely different files. Even though they're the same architecture, we would expect next to no correlation, and both of them show. The login.sh between the Ingenious and the WatchGuard device actually turns out to be exactly in the middle of 96 and 79.8%, meaning both SSD and MRSHCF failed on different spectrum. So one was a little bit higher, one was a little bit lower. What was really interesting and why we end up using MSRH CF is lines 3, 4, and 5. These particular things are naturally similar files. So SSD gives us back 0% correlation, while MSRHCF ends up giving us the small amounts of correlation that we need to make links between these particular files. So this is extremely important to us. So let's take a look at how we can use correlation to find this particular Telnet jailbreak that we just talked about in other devices. It turns out that the information that was disclosed publicly talked about 6 different devices, 5 Ingenious and 1 Arachnus. If we run this through the sample set of data that we've analyzed, it turns out this ends up being in 42 other devices from not only Ingenious, but WatchGuard as well, and also TrendNet. So it's strange to think that this particular backdoor, this particular issue that allows you to escape that particular jail ends up being in 3 different unique manufacturers. But the bottom line is that particular information is probably born, or that code is born from a lower level project like a SOC vendor supplying sample code to get these projects started or kicked off. Also, that web shell we just talked about, we can relation on that to find those particular issues in other devices as well. We knew from information that was posted online that this particular device was found in 1 Belkin device, but we found it in 28 other devices almost immediately from Belkin, Ubiquiti, TP-Link, and TrendNet. So 4 very unique manufacturers using the same exact web interface or web shell. Again, it's probably born from the SOC manufacturer supplying the code that is started from, and this information isn't stripped out prior to. Now, recently, NCC Group released information about an SSH backdoor on libSSH. So what happened was the server side was never meant to handle the SSH2 message user auth success. It was only meant to handle the request. But that code was left in there and it would process it. So if you modify your SSH client to send the message user auth success, it will actually honor that and end up setting the session state for that information. So when we query this particular device, whether or not this libSSH is existent in devices, we end up finding it in 5 unique devices from Belkin, TP-Link, and WatchGuard. Of course, there's configuration concerns about whether or not configuration settings may block that particular usage of that vulnerability, but at least we're able to narrow it down extremely quickly to the types of devices that it applies to. So the interesting piece here, this is a callback for handling that particular message type. And on indexes 16 and 17 are where that structure gets modified to indicate that there has been a successful authentication attempt. Okay. So at this point, we have taken a look at the amount of data that we have. We know what backdoors sort of look like, and we know that correlation can help us find things really quickly. But now we need to find our own things. We don't want to wait for some report to come out online in order to be able to find issues in devices via correlation alone. So we need to be able to hunt through source code and binary files for these types of issues ourselves. So when you're thinking about source code analysis and the complexity, things like pattern matching and regular expressions simply fall apart extremely quickly because they're so limited. When you think about the process of source code analysis, this concept of the Chomsky hierarchy comes up, where we have sort of 4 concentric circles or rings that represent the complexity of different language grammars. So the very middle, which is the most simplest to parse and understand, are regular grammars, which are parsed by regular expressions. They simply require a finite state machine, and that's it. When you go to context-free grammars, it requires a finite state machine plus a stack. Then context-sensitive requires 2 stacks or more memory. And then recursively enumerable requires a Turing machine. So when we're part of source code, and when I talk about source code, I'm not really talking about C and C++. That doesn't necessarily exist on these devices. It's things like JavaScript and shell scripts for startup analysis and PHP and ASP, these types of things that we're looking for. So here's an example of why regex won't work. So we have this function here that's Java. It takes one integer and it returns a string. It's called more or less. And This particular value, when you're analyzing it in statically, does not have one answer. We aren't given the privilege of state or concrete execution. So we don't know what the value of X can take, meaning we don't know what the value of Y is. So the potential values of this end up being null, more or less. And when you apply to uppercase on more or less, they become uppercase. But what happens when you apply or try to call to uppercase on a null value in Java? The answer is I have no idea. I'm not a Java person, but we have to account for all of those things. So the state of what goes on cannot be parsed by a simple regular expression or pattern matching alone. You need much more advanced analysis to do that. So the process really breaks down into lexing and parsing. Lexers are this process of breaking down the input stream of source into tokens. And these tokens or lexemes carry information about them that are tied to the grammar that you specify. So this const fruit apple is from JavaScript. And essentially what it means is that there is a variable declaration. It has more information attached to it, like what its actual kind is. So in this case, it's a constant. And then you have an identifier and literal, and you break these things down into tokens that can then be parsed later on. The parser takes these lexemes or tokens into account when it's constructing a parse tree or a concrete syntax tree. Now, the concrete syntax tree is tied very heavily to the type of grammar that you use or the grammar specifications. So things like program and variable declaration and variable declarator are all things that exist, are all things that we've named inside of our grammar. An abstract syntax tree is when we prune this tree down and come up with a more abstract sense that's decoupled from the grammar that we've specified. So to give more of an illustration of how we actually accomplish this, one of the projects that we use to generate lexers and parsers is Antler. Antler is another tool for language recognition. It's a Java-based tool. But if you develop your grammar for the language you want to parse in this extended Bacchus Noir form or EBNF form, what you can do is feed this into Antler and say, give me a parser in JavaScript, or give me a parser and lexer in Python. That way we can deploy Node analyzers or Python analyzers to do what we want to do. At that point, take the source code, feed it into the lexer, which tokenizes it, passes it to the parser, creates the parse tree. We trim that down into an AST, and at that point, and only at that point, can we really start analysis. There are tools out there that do obviously vulnerability assessments on source code, but what we found is most of those tools that we use actually in our own practices when we're developing our code is that a lot of those things tend to trigger on not so much the types of vulnerabilities that we care about, but things that relate to technical debt. So it's cognitive complexity. It's there you've defined this particular variable but never used it, or you might want to consider refactoring this code. Those things we don't care about when we're looking for vulnerabilities and issues. It's great that it finds them, but we have signatures that we actually want to find and identify. So once you get to that point, at step 10, you can start doing more analysis. And that more analysis is usually defining a scope tree. So this is if you define a variable called like source code or something on a global scope versus scope inside of a function, you need to be able to identify the difference between those two and not get them confused during analysis. All of that feeds into a symbol table that tracks the data as it goes through the execution of the application. So the data flow analyzer takes into account the declaration of variables when they get reassigned and when they're passed into functions. So we can understand the pathway between sources and sinks and try to determine whether or not a link exists, and if that link has been modified by a function that may have sanitized that particular input source. So it really comes down to understanding user input into a system, that user input making its way into a vulnerable sink, and then understanding whether or not it's possible for that to be sanitized. And only if all of those conditions are met do we actually respond with an alert that says, this is a potential issue that needs to be looked into. That way we can completely get rid of all of these like huge false positives that end up being thrown out all over the place. The pattern analyzers basically represent cases where we get down to a particular point and we know user input is being passed somewhere or data is being passed in. If we want to understand the pattern of a sanitize function, we can then run regular expressions at that point, since we're focusing on such a really small subset of the code and we know what context it's being used in. So in this particular case, you can use this to find really simple examples. And this is perhaps the most simple example that you can possibly think of. The issue that existed in the login.sh, which we talked about, is a shell script that's only 363 lines of code. So what I can do here is run analyzer on this, which doesn't take long at all. And what will happen is it ends up parsing everything in that source code file to look for blocked or guarded that look like they're launching a shell. So what we have is on these particular lines are the things that we actually care about. So we can go to 299, for example, and what we end up seeing is this. Now, you can use another expression to try to find exec and then something that looks like bin sh or bin bash or bin, whatever else. But the problem is when you do that, you end up getting so many false positives that you can't sift through all of them. So what we do is, using the parsing methods that we just talked about, is check for any particular cases where there are predicates like this that have a variable that are matched to a string literal. And then after that, the condition that exists as a child node under that branch ends up looking like an execution that spawns a shell. So what that potentially means is that there is user input or input that comes from some function that may be influenced by a user that allows execution of these shells. That means we immediately cut down on all the noise that we get, and we're only being notified of issues that are very high probability something interesting is going on. So that's extremely important to understand. We also do this with JavaScript in order to pull out interfaces to CGI scripts. So if you click on a specific node or try to look at a specific file, and you want to understand how to fuzz that or how to get information into the backend on a specific system, we can actually extract all of those things via this type of analysis. So it's not just looking for vulnerable signatures or something. It's looking for specific conditions or post things like that. So that's what happens during static analysis. Now, binary analyzers are really interesting because there's a lot of challenges that come with binary analysis on embedded systems. The biggest one is that there are so many different architectures, right? There's ARM, MIPS, and PowerPC are the most common, but MikroTik has lots of x86 and even tile devices that don't represent the kind of normal tool sets that you would deploy for binary analysis. So really what we need is an intermediate representation or an intermediate language that we can link these representations to or these things and perform analysis there, rather than having to rewrite all of these analyzers on every individual architecture. We can do this on the intermediate language. So the process that we use is to deploy microservices for each of these. And essentially, we scale these based on the amount of demand that we have for processing. So we input a binary Ninja. Binary Ninja does the complete disassembly and linear sweep. Will lift to its medium level intermediate language in static single assignment form. Then we can write our analyzers in Python to query that information and push those to Kinesis bus or Kinesis stream with the JSON information that says, hey, pick this up and start processing it or posting it into databases. When we look at the different structures of how things look in different assembly languages, it becomes apparent why we do this. We have ARM, MIPS, and PowerPC that are all implementing a square function. The square function just takes a number, multiplies it by itself, and returns that value. This looks wildly different in all these architectures. But the generalized MLIL on the right is what we get in each of those. And we can very clearly tell that R goes into var-c, which is then stored into register 2. Register 2 and var-c are multiplied, and then the value of that is returned. So it's much easier to understand what actually happens during this. So the semantic meaning is easier to reason about. Now, the process that Binary Ninja will do is when we put in binary files, it'll perform analysis that gets imports and exports, functions, cross-references, global and local variables. It'll also, at the medium level, do type propagation and basic stack resolution. What we do at that point is take over and try to do better stack analysis. And when I say better, it's basically better guessing. What happens is when when any disassembler is looking at a function, it ends up trying to understand where instructions are referencing the stack and then building those as unique variables. So if you have a structure on a stack that's allocated, and then some piece of code references something in the middle of it, it'll break that up into two different variables, but it's only actually one. So later on, if you have a mem copy that copies into that, it may look like it's overflowing the bounds of that buffer, but it's really not. So we need to try to filter those cases and understand what the potential sizes of these particular things are before we can actually do analysis on them. We can also track when allocations on the heap are allocated or freed. We can do data flow analysis and then look for commonly misused functions, and also employ checking for common CWE types, right? So let's take a look at how we end up doing frequency analysis on BusyBox for this particular issue and get a sense of how long the processing actually takes. So I have this queued up here on this BusyBox. So what's going to happen is Binary Ninja is going to be invoked and it's going to start processing. The processing time is something that's going to be required. So Binary Ninja is now opening this up and starting to analyze the ELF structure and get everything that it can. Then it does a linear sweep, and the linear sweep means that we can resolve and analyze functions that aren't called in the normal execution chain. So what you'll have is from main or init, things will start happening. If a function is registered as a callback as opposed to a direct call, we need that linear sweep to pick those things up. So now results are starting to stream in, and we see things like stir and copy 63 bytes into a 60 byte stack buffer, or unknown bytes, meaning what happens is the buffer is probably passed into a function, and then that function ends up using that information that's passed in to copy to a stack buffer. So we can't actually resolve that until we do more analysis. And in most cases, we can't actually resolve it at all. So what's actually coming in here are some other things that we look for, like mem copies, stir and copies. These are things that are interesting to know as far as like what's actually happening. And then we see the string that actually just popped up. So if somebody who's looking for issues in software end up just running strings, they're going to find a bunch of junk that doesn't matter at all. What ends up happening here is we can take this information that comes out of this and go through all of the BusyBox samples that we have, do the sniff analysis, figure out what gets referenced in stir and compares and stir compares, and then go to the actual BusyBox project online, download all of their versions, and perform the same frequency analysis. And then what we end up doing is doing that, the difference between them. So if we take the 9,574 unique versions of BusyBox that we have, run this through our analyzers, take the full, there ends up being only 741 strings that are actually passed to stir and compare. And then we take the difference of everything that exists inside of normal BusyBox builds out there. We can start to see patterns emerge from the types of things that are implemented for and built into custom versions of these BusyBox things. Strings that probably shouldn't be there, or strings that indicate functionality that's unique to that particular device. Then we can use that in validation that is not a backdoor credentials. So using this type of analysis allows us to quickly do that. Now there's one last demo. This demo is interesting because it talks at the flaws of static analysis. One of the benefits of static analysis is that we can analyze every piece of code. It doesn't matter if we can actually get to that location or not. And it'll analyze dead code or code that can actually be reached. So the problem that we have is, although we get all of this great code coverage, once we're done with the analysis, it becomes a problem of trying to solve to that point or validate that code can actually be hit. So what we're looking at here is an ASUS device that uses this feature called Download Master. It's implemented into ASUS Lite HDBD, their custom version of Lite HDBD. And it ends up being that what you can do is pass a certain meta tag into this particular device and trigger buffer overflow that will allow command execution or control over the instruction pointer. So let's go ahead and run this analysis. And when it comes out, we'll take a look at it in Binary Ninja. I'll explain what's actually happening here, and then I'll explain to you how it's completely useless. So it ends up being a problem that if anybody's doing static analysis in these types of systems, there is no guarantee without verification that it impacts security at all. So it's dangerous to just assume that issues that we find during this process are directly applicable to that specific device in its specific configuration without an actual execution state. So that becomes the actual problem that we need to solve after this. It's easy to find bugs. Everybody can find bugs. It's hard to validate bugs when you don't actually have the system, or emulation takes a lot of time and effort to accomplish. So this will be done here in just a few seconds, and then we can jump to the location. So I know just by seeing this and running this before that this is the problem that we're looking at. So it does say that we've copied an unknown number of bytes into a 512 byte buffer. And if we go to this location, 1F8 CC right here in Binary Ninja, what we end up getting is to this function, get raw URL. So get raw URL takes one argument. It actually has just one variable, which is if we take the difference between 218 hex and 18 hex, ends up being 512 bytes or 200 hex. What we're doing here is taking this stack buffer and then setting it to 512 null bytes, and then looking at the input, which should look like this, which is meta, HTTP, refresh, and this information. What this does is it parses out this information. So everything in the URL equals here. So if we can supply this URL equals this string here, if we can input that, that's larger than 512 bytes, then we will go over the bounds of that buffer. And then once get raw URL returns, we'll have control. So this information is what we're interested in, and this is what we want to try to get to this system. So we found the issue, it's easy to identify, but now we have to try to solve backwards to see if we can get user control input into this at that point. So the issue is down here. And the problem that really stems here is that N is actually calculated based on the source buffer. So the input buffer is calculated from the start and the end of the URL. That comes from these two chunks right here, where it's actually looking for that. And then what happens is it ends up putting all that information into a 512 byte buffer based on the size of the source buffer. This is a huge no-no, should never be done. And it's one of the common mistakes that we end up looking for and seeing quite often. The problem in this particular case is if you try to get to that location, it ends up never triggering, at least in nothing that we've ever been able to solve or do on a live device. I only took a few hours to try to validate it, but the problem is we cannot, through static analysis, imply that any of the bugs that we find are a threat to the infrastructure of some organization without validation. And if we make that assessment on risk, we better be sure that we can actually do it, which requires much more advanced analysis. So I don't want to come out here and say that finding backdoors is this easy thing. Finding indications of backdoors is really easy. Validating and proving them, especially on devices that you don't have access to, is really difficult. So that's kind of like brings us to the end of this sort of the whole world of what we're looking at. The research summary is, again, 4 verified IoT devices that target 75 unique, 4 unique backdoors, 75 devices, 11 we're still working to verify, 107 devices, and then we're trying to work with manufacturers on getting this information to them. The problem that we think that we're encountering is that manufacturers don't want to know of potential bugs. They want to know of vulnerabilities. So they need to be proved beforehand before we can do that. And then we also need to track what the status is of all of these particular devices are. So that's kind of it. I know it's a lot of information about the process of performing static analysis here. Hopefully it gives a sense of the types of research or the types of work that you can employ for static and dynamic analysis against these things, and type of patterns that you can look to try to identify backdoors. So with that, I'm done and open to any questions that you might have.
Thank you very much, John. Any questions from the audience? Yes. Because he's on Skype, we will have to actually convey his question.
Yeah. Okay.
So, but just
Yeah. Yeah. Interesting research, and I was wondering if you are going to share the code or the tools you've created.
can you say that again? Sorry.
Oh, sharing the code and the tools we created is what you asked?
Yes.
So we are looking to potentially do that for segments of our code, specifically the source analyzers and tools back into Binary Ninja plugins. It's something that we're a really new company, a startup that's been around for about a year. So we're still trying to understand which pieces are sort of most beneficial to open source and which are not from like a competitive standpoint in the market. It's something that I've done in the past on other tools, and certainly will continue to do in my own personal time. But I can't answer that question in terms of the company just yet. But I know that it's something that we're very interested in doing, working with the community on tools that can help this research and individual researchers. Thanks. Yeah, please try to contact me later on, and hopefully I can give you a status update on that.
Okay. Thanks.
Thanks.
Any other questions from the audience for John? No? Well, okay. Well, John, I believe that's it. Thank you very much for taking the time to do this presentation with us via Skype. And again, we're very sorry not to have you being able to join us, and sorry for the hiccups earlier before we started today. Thanks a lot.
Thank you so much.